4.7, number 1. A rectangular storage is to have this, okay? You have a rectangular storage with open top, which holds 40 cubic meter, 45 cubic meter. How big is that? Oh, it's a container. Okay, that makes sense now. The length of the base is twice the width. Okay. And then you are going to build the container, which means you need to build the base at a price of 12 per square meter. And you want to build the sides with a different material, which is cheaper. Okay. Find the cost of material. Of the cheapest such container. All right. So basically you have a rectangular container. It has a fixed size in terms of volume, but you can build it to be shallow or thin. Okay. Meanwhile, however you build it, you want to make sure in the base, the length is twice the size of the width. All right. You want to minimize the price. Therefore, you should have a formula of the cost or price. The cost is going to be the cost of the base plus the cost of the sides. Okay. There's no top, so good news. For the base, it's going to be this much per square meter times the area of the base. So you start to assign variables, very typically x, y, and z. Then it's going to be x times y. Okay. For the sides, you have 4 sides. 2 of them are going to be yz. 2 of them are going to be xz. So it's going to be 2 xz plus yz. Good so far? Okay. Of course, we cannot do it because we have too many variables. Now it's time to use our condition. Number 1, the length is twice the size of the width. Depending on how you call the length, I would just say y equals 2x, which means y is the length, x is the width. Second, no matter how you do it, the whole volume has to be 45. So x times y times z has to be 45. Sounds good? With all this kind of setup, you should be able to know, okay, if I see y, I replace it by 2x. If I see z, I replace it by 45 divided by y and x, which is 45 divided by x times 2x, which is 45 divided by 2x squared. So you have y, you have z, but now they're all in terms of x. So cost. xz x 45 over 2x squared plus yz. Good so far? That will be it. This is the one you are trying to minimize. The rest is try to find the derivative, take the derivative, set it to be 0, find the x. All right, 2 times 3, 6. 6 times 45 divided by 2x, which is 13. So this is going to be 135 over x after simplification. Let me just make sure. Yeah. Yeah. Okay. Then well, can I simplify more? Both divided by 3, that's 16. That's 45. Yeah, that's it. All right. Now what you want to do is put everything here. Try to do it. You find it's negative and positive. So clearly this one was a minimum. And you were looking for cheapest price. So that matched. Finally, what's the cheapest cost? Then it's going to be 24x squared plus 135 divided by cube root of 16 over 45. Whatever that number is. Try this. If Weber doesn't take it, try to do the decimal using a calculator. Testing? Okay. Other questions? All right. We finished 4.7. We did all the applications of optimization, which is pretty awesome. And 4.8, now we're in 4.9. Antiderivatives. Okay. We briefly talked about this one in mean value theorem, but basically the idea is if I know it's x squared, I know the derivative is 2x. But now if I know something, its derivative is 2x, can I say it is x squared? It's like the inverse operation of taking the derivative. That's why it's called antiderivative. Okay. Can we? The answer is no. Even x squared qualifies. There may be other function whose derivative is also 2x. So x squared is not the only answer. Second, according to the mean value theorem, it won't be much different either. It's x squared plus c. X squared plus 1 works. X squared plus pi works. X squared plus any number will work. So as far as you can see, what's your answer? My answer has infinite many elements. Okay. But they all look similar. That's our answer. Sounds good? Another way to think about it is this. What is the derivative of this? Well, clearly the derivative is this. Good so far? But if I erase this one and tell you this is the derivative of fx, what do you think the original fx is going to be? Well, all I know is the slope is 1, right? So this one works. Good so far? But can you see that this one also work? This one also work. This one also work. This one also work. As long as you keep the same shape, you just move up and down. Okay, your derivative, your tangent rate doesn't care where you are. It just care about where you are going next, the relative position. Okay, from here you can see where the plus c come from. Plus c basically means shift up and down, and it doesn't change your derivative, which is true. Sounds good? Okay, so that's roughly the idea of the whole section. Now we just need to write them down, write them all down carefully. Number one, what do you mean by antiderivative? Okay, well, definition. Fx is the antiderivative of fx if the derivative of f is equal to the small fx. Straightforward. Number 2, the factor we wrote down. Fx is not unique. There can be many functions who all give you the same derivative. But usually it's giving a format. Actually, take it back. It's not usually. Always it takes the format fx equal to some function plus a constant. Okay. Keep in mind, this constant can be anything. So what you see here is really not just one function. What you see here is what we call a family of function. With technically infinite many number. So it's a big family. Let's just use member. So you're talking about a lot of function, x squared plus 1, x squared plus 2, x squared plus anything. The reason is because if f prime x equal to 0, then fx equals c. That's the corollary we got from the mean value theorem. This one guarantees that if there is any other function who has the same derivative as yours, the difference will just be a c. Sounds good? All right. That's the definition. Now let's try, can we go ahead and try to find the antiderivatives? Okay. Let's take an example. Find the antiderivative of the following. Let's divide them into several categories. Number 1, what's the antiderivative of 3x squared? X cubed. What's the antiderivative of cosine x? Oh, sin x plus c. What's the antiderivative of 1 over 1 plus x squared? Looks familiar? What is it? Tangent inverse. Do you see how to do this? Do you remember you have a formula sheet of how to take the derivatives? Now you just take the same formula sheet, but going from the right to the left. That's basically what you're looking for. Of course, when you finish, plus a c, always. Okay. Nick?
I know you said arctangent, but couldn't it also be ln?
What's the derivative of ln?
1 over x, right?
Yes, therefore, the antiderivative of this is ln. Can you see they're different now?
Okay, yeah.
Yeah, but I kind of get what you mean, so I will give you an example after that. That is actually what's the derivative of this? Antiderivative of this. Because I see you were trying to say that, like, if you have this, if you take the derivative, clearly you have 1 over 1 plus x squared, right? So it's possible. But
Yeah.
a second thought, not really, because you have to have this by the chain rule.
Okay, yeah, that makes more sense.
Right? So actually, your question is perfect because then people are going to ask, well, this one produced that, this also produced that. But like the theorem we said before, no. If you both produce the same derivative, you guys look exactly similar. Okay, so you should root this out. If this works, this won't work, even though you haven't checked yet. Unless you guys look extremely similar except for a difference of constant. Okay, so that's a very good question. But second thought, they will have different derivative. Is this part okay? We don't need more examples, right? Just go to your formula sheet. Okay, every time you just remember, like, for example, secant square x. Totally familiar. Okay, totally familiar. That's tangent x. Okay, it's just get used to it. You're going from the right to the left. Okay. So first case, just formulas. Second case. What's the antiderivative of this? Well, what's the antiderivative of the first one? X cubed. What's the antiderivative of the second one? Sin x. Can you just add them together? What do you think? When you take the derivative, you can add them together. What about when you take the antiderivative? Of course, you can add them together. So we have the f plus g, f minus g case already, right? If you have plus or minus, period, it's done. Okay, good. Second question. This one goes with a C. This one goes with a C, and we shouldn't call it C anymore. We should call it D, just to say that they're different. Good so far? Now, does it look? I mean, if C can be any number, D can be any number, can you just merge them into one? And just use one C instead? Of course you can. Then, no matter how many terms you have here, even though you have many C, okay, you can eventually merge them into just one C. Good. So plus is not a problem. Minus is probably not a problem. As long as I know this is, and this is, and then plus a C, everything will be okay. So plus and minus is okay. What's the antiderivative of x squared? Technically, I know this. Right? If you have 3x squared, that's going to be the derivative of x cubed. Good. What about just x squared? Number one, it can't be this because the bottom line is this. How do we modify it? Just times 1/3. Does it make sense here? Think about it. How do you do this? How do you take the derivative of 2x squared? Well, you just take x squared, and then you just times it 2. Right? So how do you take the antiderivative of 4x? Well, you just do the antiderivative of this, then you times it 2. Make sense so far? So if you see something similar to before, and the difference is only a constant, you just times the constant to cancel that thing, period. Let's try some examples. Okay. What's the antiderivative of x squared? Well, it's coming from x cubed. But if I take the derivative, I have this. I want x squared, so let's take a 1/3. Okay. It's going to be x to the 5. But if it is x to the 5, I take the derivative, I should have this, right? Then just times 3/4. Make sense so far? Okay, so you just match the constant. You can do multiple ways. Personally, what I like is I just take this one, which will be more than 90% of the answer, then take the derivative back to see how much constant did I miss, and then just go ahead and do it. Sounds good? Okay. What's this? Good. But this, if you take the derivative, matter to. Okay, let's do it again. I start from here, then I guess this will be my answer. Okay? But there may be a difference of constant. So if this is my answer, I take the derivative, I should have this. Still okay? But I don't. I have this without the 1/2. So what happened? I must have timed the 2 somewhere in order to cancel this. That's how I do it. Sounds good? Try this. Step 1. Good. Step 2. Can you see why? That's how you do it. Which is x to the negative 3/4. Take it back 4/3. All right. Oh. Does everything make sense so far? You are not super proficient with this right now because it's kind of like, number 1, not hard. Number 2, it's weird. Okay, do some exercise until you get used to it. Sometimes you go this way and sometimes you go this way. You take everything exactly the opposite. Okay, 3 means 1/3. Okay, 4/3 means 3/4, things like that. Do some exercise. You will get used to it. But basically, what we finished here is, number 1, we have formula. Number 2, we have f plus g and f minus g, and it seems to be okay so far. At a constant times f. Sounds good? Then you know the drill. F times g, f divided by g, f circle g, period, done. Okay, we have 3 more to go. Very quick. Number 3, actually. Let's do f times g. What's the antiderivative of this? Same logic. The antiderivative of x, 1/2 x squared. The antiderivative of e to the x, that's e to the x. Okay. Can you just multiply them together? Then you need to ask yourself, if I take the derivative of this, what should I do? Do I just take the derivative of the first, take the derivative of the second, and multiply them together? No, you don't. You do product rule. Make sense here? Okay, so this is not easy. It cannot be done as easy as this. So multiplication failed so far. How big is my, okay, then this should be, okay. So not easy, not straightforward. Can you guess what it is? Try on a paper. Try to make it happen. If you finish, just raise your hand. That's what we want, right? But we have a leftover. But then we just minus the leftover. Okay, if you take the derivative of this, it produces two terms. One term is what you want. The other term, we get rid of it. Okay, try that. This is the answer. Sounds good? Easy? You must be really lucky for this case, right? If I give you a general case, it's not so easy to do this. So this is not easy. We save it for calculus 2. This is called integration by parts. So for our class, we don't even handle it because it's complicated. Okay, similarly for quotient, we do the same thing. Once you know the product, the quotient is easy. So product and quotient, calculus 2. Save it for later. Okay, then there's only one more left. What's the antiderivative of this? Do you observe something special? These two has a relationship, right? What relationship? The derivative of x squared is to x. So what are you witnessing here? You see a function times the derivative of the inside. That's the chain rule, right? So if you're going to make a guess, the guess is going to be this. Why? Because if you do this, first you do cosine, second you times the derivative of the x squared, which is 2x, which happened to be this case. Sounds good? That's how it's done. Back to Nick's example. What do you see here? Well, technically you see two things. This one equals 2x times this. Moreover, this one is the derivative of the bottom, right? So what you should really see is, you just see 1 over something and then times something prime. That's a hint to tell you this is ln. Sounds good? Okay, keep going. Cosine e to the sin x you see, this is the derivative of this. So what you're looking at is e to something times something prime. Okay? And your focus should be on e to something. So this is e to the sin x. Does everything make sense so far? Okay, can you see this one's harder? This one involves chain rule. What should you look for? You should look for the majority, the major part, and a leftover, which give you the derivative of sum of the part before. That's how we got the chain rule, right? So what you need to shoot for is something which is like a pattern, and then the derivative of that pattern. That's why it's hard to recognize. We will do this. Use something called U substitution. That is going to be the end of chapter 5. Okay. For now, we don't concern too much about it. We have a whole section later to handle this. Okay. We probably need a clever way to write down some steps to let us recognize what's going on. The harder part is not doing it, is the recognizing thing. Recognizing x squared and 2x, recognizing sin x and cosine x has a relationship. Sounds good. That's it. That's everything we need to know of how to find antiderivatives. Now let's just do 2 more examples. Okay, 2 types of questions. Nothing new, but just some quick example. The first one, we call it the initial value problem. So basically, if I tell you f prime x equals 2x, your best guess is fx equals x squared plus c. You have a constant which is not fixed. It may come from some stock price. It may come from some weather you recorded or something like that. You got this thing and you solved it. Good so far? But in real life, you do want this constant. You don't want some random constant. So what you can do is you can add 1 piece of information. You tell people f0 equals 2. Just 1 additional measure. Or maybe you tell people f2 equals 4, something like that. Good so far? Once you have that, what you can do is you can plug this one into this one. And once you solve it, you will have a fixed number for this c. So it's more about knowing 1 piece of additional information will help you to narrow down the selection of the constant c. But without that information, any c is possible. Good so far? It's the same thing telling you like, okay, today is 10 degrees higher than yesterday. What's the degree of today? 30, 40, 50, 60, all possible, right? But if I tell you today is 10 degrees higher than yesterday, and yesterday was 23 degrees, then suddenly all the plus c thing is gone. Today is 33. Okay, so you just need one piece of information because just knowing the change, it only tells you the relative position, not the absolute position, right? If I tell you I increased from yesterday for how much, I still need the baseline, I need the benchmark, I need where you start with. That's the initial value, okay? Another way to think about it is this. If you know the derivative, you can still move it up and down. That's what your plus c is, right? But if I know, okay, not only you have the derivative, you also need to pass this point. Just one point. Then what can you do? There's nothing you can do. This one, you need to just move it up all the way until here and you stop. A little bit higher, won't do it. A little bit lower, won't do it. Only this one will do it. So there's no plus c. There's plus 1.3 or a fixed number. Good so far? Okay, so that's how we use antiderivative in real life. You need two pieces of information. The first one is f prime x equal to something. The second one is you need a piece of information. Just one piece of information to help you to figure out what c is. Sounds good? Let's try a quick example. If I know f prime x equals 3x to the cube, and I know f0 equals 2. Okay, find fx. Okay. Very quick. It should be x to the 4th, right? But if I do that, I'm going to produce a 4. So I need to cancel the 4. I need a 3, so I put a 3 here. That's my fx. Good so far? One more information, this. Well, then this implies c equals 2. So final answer. There's no ambiguity anymore. Sounds good? Beautiful. Second case. If I give you the derivative, you know how to find the original function. What if I give you the second derivative? For example, if I know f prime prime x equals 10 times t. Actually, f prime prime x equals 10. Can you find fx? Can you do it? Well, let's find f prime x first. I don't know how to do antiderivative for second derivative. I do know how to do first derivative. But if I treat this one as a first derivative, I'm not looking for fx. I'm looking for f prime x. Good so far? Okay. What's the antiderivative of a constant? That's just going to be the constant times a t, x, plus a c. You take the derivative, you got 10. Good so far? Can you do this now? By taking the antiderivative of this. Okay, what's the antiderivative? That's 10 times 1/2 x squared for the first case. What's the antiderivative of this? Ct. It's a constant, right? Plus another constant coming from taking the derivative again. Nick?
Wait, why would it be CT? Wouldn't it be CX?
CX, yes. Thank you.
Oh.
Keep doing that. You're right. Make sense to everybody? You have the first constant. The first time you take the antiderivative, it can be anything. You have the second constant coming from the taking the derivative for a second time. So you do have two free constants now. If you think about it, it totally makes sense, right? Before, why do you have a plus c? Because once you take the derivative, the c is gone, you have 0. With c, without c, you got the same answer. Okay. Why do you have a cx plus d? Because if you take the derivative for twice, you have c plus 0, and then 0. Your information is gone, right? That's why you can have two constant here. So that's the answer. Where c and d can be any constant. What if I give you the third derivative? You just do this for 3 times. Okay, every time treat 1, and then again, and again, and again. Every time you do it, you produce 1 constant. So if I give you the third derivative, you give me 3 constant. 3 degree of freedom. You will have a constant term, you will have a t term, you will have a t squared term. Because after you take the derivative for 3 times, they're all gone. So with them, without them, they're all the same. Sounds good? Question. What if I also want to do an initial value problem? I don't like C and D. I want to know what C and D are. Can you see? You just need to provide additional information, like before. But you need 2 of them. 1 is not enough. Good so far? Usually, what people give you is F A equals B, and they give you another thing about F prime A, or maybe F prime C and equals D. Either way, you just need 2 pieces of information. What about third derivative, then 3 pieces of information? Okay, the idea is every time you take the derivative, you kind of lose 1 information. You need to add it back. Sounds good? Pretty easy? All right, now let's use something. Do you realize what you just solved? Take a look. Have you guys solved the free fall problem in physics before? Okay, what you have here is you have some guy who's standing here at the top of the building or something. Okay, this is H. What he does is actually he throws a rock, and then the rock is gonna fall. Good so far? Okay, do you remember the formula? You don't have to anymore. You just let Ft be the height. Of the rock. So it first goes up, then goes down. Okay, eventually your height becomes 0. Good so far? Okay. What is F prime t? The change in rate of the height. That is going to be the velocity. Good so far? All right. Then what is F prime prime t? That's going to be the acceleration. Good so far? Okay. Newton's second law, F equals ma. You already know the x. Ah, shit. Why do I use F? Let's use H. Okay, F equals ma. Then you have F equals ma, right? What is your F if you are doing free fall? What's the force? Gravity. Good so far? Okay, now what's the trajectory? Well, H prime t. equals gt plus c. Okay, h prime prime t equals 1/2 gt squared plus ct plus c. D. Does it look familiar? That's exactly what you get from physics class in junior high. Okay, but instead of doing this, they told you the formula. If you do constant acceleration motion, then you're going to have gt and 1/2 gt squared. Okay, but this is actually where it comes from. You just take the antiderivative twice. Okay, as easy as that. Good so far? Now, do you recall when you try to do those kind of problems back in physics, they always give you two conditions. They tells you the initial height, they tells you the initial velocity. Make sense so far? They tell you h0. They tell you h prime 0, which is your initial velocity. Why? Because without that, you cannot find the constant c and d. Then you still don't know everything about the motion. Sounds good? If you think about it, if you're standing on the thing, if I just say you toss a rock, how do I know when the rock, where the rock is? Number one, you have to know where did you stand? Did you stand on the ground, or did you stand on the mountain and toss it? That's going to be different. Okay. Number two, what's your initial speed? Did you actually toss the rock, or did you just let it go, or did you just actually throw it down? That will make a difference, even though the whole motion will be the same, described by the same differential equation, basically. Yeah. Okay. But with that two information, then you know everything about motion. There's no ambiguity. That's basically you're trying to fix these two constants here by giving me additional information. Sounds good? Okay. Actually, in real life, taking the derivative is really nice, but sometimes working backwards totally makes sense, because once you take the second derivative, you have the acceleration. What people do in real life usually is they start with the acceleration, they come back to the velocity, and they come back to the original displacement. That's exactly antiderivative. It's very rare you will actually know the trajectory and then take the derivative to find the acceleration. It's always the reverse. Sounds good? That's how they figure out the trajectory of the sun. The trajectory, not the sun, the trajectory of all the planets around the sun. You know the force, right? Once you know the force, do it. You start from acceleration, you get a velocity, you get from the velocity, you get the trajectory, and then you realize suddenly, wow, the velocity and the trajectory give you an ellipse. That's basically what Isaac Newton did. Okay, do you guys know the story about Kepler and Newton? Yeah, Kepler basically think, okay, every planet, how do I do that? I don't remember his name, Ptolemy, something like that, a guy from Greek. He thinks, okay, here is the Earth, and everything is just going around Earth. Certainly that's wrong, okay? Then Copernicus, they actually say this is the sun. Everybody go around the sun. Okay, we got Venus, we got Mercury, we got all these kind of 5 planets. Good so far? Then what Kepler did is actually he looked into all the trajectories. Back then, they only know 5 planets. That's 4 planets, actually. He found they actually match perfectly with something called Platonic solid. He said, this is great. Okay, everything is a circle, everything is perfect. We're created by God because everything is so harmonic. Then he went to his teacher, his advisor's house, which is in Denmark. His teacher did nothing but recording all the positions of the sun, of the planets during the past 12 years. He just looked at the giant data table, just take a look, day after night. And then he figured, wow, shit, the trajectory is an ellipse. Okay. Then he just said, well, I have my 3 fundamental law. I have the ellipse. And every planet goes around the sun in ellipse. That's by observation. Good so far? Meanwhile, Isaac Newton, what he did, he invented calculus. The moment Kepler published this, Newton just looked at that and say, well, technically you don't have to observe that. Just according to my equation, I take the derivative, antiderivative for twice, I got ellipse. Kind of makes sense here. So what he did is he did not start from observation. He started from the law of gravitational force, which is related to the acceleration. He take the antiderivative for twice. he found the trajectory, and the trajectory happens to be an ellipse. Sounds good? That's the first time people actually, in the history of science, that they purely derived some scientific fact without observation. They get it from mathematics. And that tradition has carried all the way down to even nowadays. That is called first principle. Okay? You don't start from experimentation. You start from simple law and simple assumptions and use mathematics to derive what should be right in real life. Then you go there and measure, and magically for the past 300 years, they all matched. Okay? So that's roughly the idea of doing this. We are right on the edge of doing something interesting. Sadly, in our class, we cannot do that because it's a math class. Math class is supposed to be not fun. And it's up to you guys, actually, because, you know, every time I teach mathematics, is always the conflict, right? I teach you something interesting, then I don't have time to talk about mathematics. I teach you everything about mathematics. It's super boring, right? You don't see why you're doing this. Okay. So I would say I will leave it up to you. You're right on the edge. Just go one more step outside class. Try to see, where does people use optimization? Try to ask, where does people use antiderivative? And just Google it. You will see some interesting thing. Sadly, I can only go over so much in class. Okay, so keep in mind, if you ever find this class boring and not useful, that's because we teach it in this way. Just do that one more step. You will find it opens a whole new door, okay, to everything that is interesting. All right.